Thank you, Max. I'm Bhupendra Raut, and I work in Northwestern Oregon Institute of Science and Engineering. And this is my first SciPy, and I'm already so excited. I think I'll be a regular visitor in the SciPy. And you can see this is our team that works on Tobac, and there are many people from different countries. Max is in Oxford University, and Max Heikenfeld, who is also from UK. There are people in Germany, so this is a very international collaboration that's going on. We have around 13 people in the core developer team, and we have around 35 members in the community. And this software is developing very fast, and we are having many ideas, and we really want to know what are the ideas that we should be pursuing. Bobby here is with me. Bobby is in Argonne National Laboratory, and once I present the first part, Bobby will be taking over for the second. So why to track clouds, and why it is so important at this time? So you can see that people were tracking clouds since like very long time, and they wanted to study it because there are two domains and two ideas of the studying this kind of dynamical systems. Is like an Eulerian domain where you basically take a region and study how everything in that region change. So it's more like a statistical way. And then another way is actually to track the individual object. That's a Lagrangian way in which you track the object and study the life cycle of that object, how it studies. And you will see, if you look at the research papers in like last 50 years, you will find that 99% of the cloud studies and rainfall studies, where we are actually studying life cycle of the system, are not done with using the Lagrangian studies, but they are done by using the statistics of the large number of clouds at a time. And why is it done like that? Isn't Lagrangian the better way? Well, it is. The problem is tracking a system is quite a hard problem, and it requires very specific algorithm for a specific kind of objects that you want to track. For example, if you want to track cars, your object really need to take care of occlusion, and cars are rigid objects, so they don't change their shape and size much. But in case of cloud, it's different because cloud changes their shape, size, values of reflectivity, as well as there are other complexities because the clouds split and merge. So you also have to take care of all these issues. So many people have developed these algorithms with some advantages, some disadvantages, using different methods. The trouble with that is that all these algorithms, none of them, you can think they were accessible. So most of them were not open source, and those which are open source are hard to implement because they have restrictions on certain kind of data, because they have restrictions on certain kind of analysis they do, so you can't do it flexibly. And so therefore we have these efforts to study, to do the analysis in a way that you will have flexibility, but you will not have to do all the hard work that goes into that. So the reason that there are lower number of studies with tracking is because either you have to do a lot of hard work or you cannot do it with more flexibility. Now, why cloud tracking is such an important, and why we are focusing on cloud is because clouds are one of the largest uncertainty in the climate model, and understanding these physical processes in Lagrangian domain will tell us a lot about the sources of errors that happens in the climate model and weather forecast model, that because of which tracking clouds in the models and in the observation both using the same package is also important, which is not currently possible with any of the existing packages. So I already told you about all the good and bad things about the current packages. So what was happening is that there were two packages actually we were developing. So Tobac is the package that Max Heikenfeld was developing, and he was using a modular approach in which you will be able to plug in and put more methods as you want your analysis. And I was developing the similar tracking package in Australia, which was actually separating each of this stage and adding it as a separate program. And we are now, this is like an announcement, like official, that we are now merge these two packages, and what we made is Tobac 2, which currently we are presenting Tobac 1, and we are working on Tobac 2. So what Tobac does is it gives you, so it's a modular structure, so it has every step of the analysis is a separate module. That means you can add your own steps. You can choose your own way of analysis, and we can add more and more algorithms in this, so you will have more freedom to choose your workflow that is more suitable for the analysis of your model data or radar data, and whether you want to compare them together or not. So Currently, this is one of the, you can say, standard way of doing analysis in Tobac, where you have input field, which get filtered. There are a lot of image processing operations that you can use to filter the data, to filter your object as you want, which could be a convection. You may want to extract only a particular kind of rainfall type, that is convection, or you may want to do all the rainfall tracking at once. So you use different thresholdings, and you can detect the features, and then those cloud areas contours are tracked in the original Tobac algorithm. And then there are post-processing analysis where you can do, you can find out how the life cycle of these different tracked system have been changing with time, or what is the statistics of these life cycle of this cloud system. And so some of the good thing about Tobac is that it's a data agnostic. That means you can have any data, because traditionally when radar data, clouds were tracked in radar data, they were expecting that everything is radar grid and it has reflectivity as a value. Now you can track radar data, satellite data. You can also track your model data, and then you can compare all these tracks and their statistics and say, okay, whether models are getting the duration and longevity, or duration and the number of the system correct, or it is, if you do the area average calculations, and you might get the same rainfall in both the simulation, and one simulation might be actually generating clouds with proper lifestyle, and other may be just generating more clouds with shorter run, and you will still get the same rainfall. But those errors actually affect or your calculations made for the predictions and the climate change scenario. And so that is very important. So you can do this kind of simulation. Other thing is you may have 3D radar data, which can also be tracked using Tobac now. And because of the modular framework, you can bring your own method for extraction of object and put in there. You can also add post-processing methods. We have recently added splitting and merging of the system into the Tobac. And so there are a lot of developments happening. We are making it faster, more scalable, and it was developed for a small radar domain, but now you can also track clouds from the larger domain, like the kind of simulation that you were seeing from NASA, which has huge domain and there are thousands of objects. So we can actually track. I don't think I'll be able to show this animation. I tried it several times, but this is like a large full Earth image in which you are tracking all the clouds that are there present that you want to track. So these are the clouds that were extracted, and then they were tracked for some time. So you could track like hundreds of objects at a time, even if they are large, over the larger domain. So there will be no confusion between which cloud it is tracking. It gives it a unique ID and it saves all the data. And as I said, we were developing TINT package, which is now part of the Tobac package. And you can get, in the Tobac 2, you have a choice to use either TINT tracking, which is slightly different from the Tobac tracking. Tobac uses overlapping. But TINT is more optimized for the smaller objects that are in high density, where there is a lot of possibility of confusion. So it uses a very specialized cost function to reduce that uncertainty whether you are tracking the same object in the step-by-step or not. And Bobby actually did this work. He merged the TINT and Tobac, so he has a lot of experiences to talk about. This is one of the simulation from the TINT example. And I hope that you will enjoy the demonstration that Bobby will show. So enjoy the conference.
Okay. So what we're seeing here is an example of next-rad reflectivities taking over the Houston area. Now, particularly here, we're focusing on Houston because the Department of Energy Atmospheric Radiation Measurement Program is currently running a field campaign called Tracking Aerosol Cloud Processes, and it is like tracer project. So basically what it's looking at here, what we're doing during tracer is that we're actually seeing how these clouds and convective cells, as they develop coming from the ocean, they develop as a result of the sea breeze over the Houston area. And when you get that sea breeze coming in, you get this front that forms. And then over along this front, you will actually have these storms that develop as you get the sea breeze here. So we have a natural laboratory for looking at what happens to the convection, what happens to all these thunderstorms as they pass through the Houston, as you go in from a clean air mass to a polluted air mass. And part of that is going to be experiments that we're running Tobac and TINT on the data to see how the cells evolve as the storm goes over Houston area. So we can see an example here of TINT being able with the new Xarray framework that is available in Tobac, tracking each of these cells as you go over the Houston area. And as you can see, there are at least 30 cells present in about this 1 hour sample, and they're moving from the southeast to the northwest in the direction of the Galveston Bay. So we are expanding our library of methods. So as I said before, we incorporated Bhupendra's TINT library, as well as we're rethinking our modular structure based on methods to one based on data structures and interfaces. And we're working on switching over our system to Xarray. Right now, a TINT we have with some of the main Tobac is an iris, but we're going to be doing it all based on Xarray, and we're working on having it be entirely based on that. So community-driven development. So since release, Tobac has been used for a wide variety of research, including clouds, storms, and models, and its satellite observations, dust storms, and baboobs, as well as tracking air pollution events. It has had over 30 citations since being released in 2019. And having a community of active users helped drive this further development. So now instead of thinking of hypothetical uses, we can focus our work on common experiences. So in summary, Tobac is an open source community-driven module for detecting and tracking objects in any gridded atmospheric data source. And it originated for a need for a more Pythonic approach to detecting and tracking clouds, making use of the scientific Python ecosystem. And it's rapidly developing through community efforts. So if it doesn't do what you need, we can probably just ask one of us or Will, and we could probably add it. So now I will go here and I will show. So you have that example open? Yeah. In the next few, we only have probably about 5 minutes left before questions, so I will briefly go through this time to look at an example code of how Tobac will go ahead and track these clouds. So I'll zoom in, because this is small. Maybe even one more. Yep, there we are. And now I'm closer to the mic. So so we're looking at this example notebook. Here as we go down. We do our imports, so it's right now dependent on Iris and NumPy, but Tobac itself is right down here. So import Tobac. And we download the example data. We have an example data record that is available as part of Tobac. So here we're just going in the code to download it. As we do, we load it as an Iris data cube. Then we're working to migrate all this to Xarray. The TINT actually is already in Xarray, so if you're using TINT, you're set with that. And this is going to be outlowing long-wave radiation for the satellite data. So that should be approximately related to the cloud top height. So we set up a directory to save and make our plots. And then we start getting the temporal spatial sampling of the grid data by doing get spacings. It's set up parameters that we want to use. So whether we have different parameters on Tobac that we could set, that you could customize the way it tracks based on what thresholds you want to do, or whether you want to look at the minimum or maximum within a given contour, and whether you want so much variability in number of points. So, for example, we have to have at least 4 points, and we're looking at the minimum brightness going long way OLR brightness temperature here within the structure. So then now we do the feature detection and save it to an HDF file. And then next, after feature detection, after detecting all those different features of OLR, we go ahead and do parameter segmentation, where we look at the target. We're again looking at the minimum, and we're looking at anything that's going to be 250 Kelvin or lower in terms of the target. So we're looking at all brightness temperatures lower than 250 Kelvin. Segment the images based on that and make the mass. And then from those segments, we look at the trajectory. We make the trajectories together using TrackPy, and it saves it to an HDF file. And then for visualization, we plot just using standard CartaPy routines using Tobac map tracks to go ahead and map all the different tracks that are present within the sample within that sample. So that's about how you would use Tobac over here. This is at least I'll give you one little small example of how to use it. If you want to learn more about it, you're welcome to talk to me. You're welcome to talk to Bhupendra or to Will, and I will go and leave it here for questions.
Alrighty, at this time, we'll go ahead and move to questions. So I don't see any in the chat quite yet. Is there anyone wants to ask a question? If not, I'll ask one. So you mentioned that this has been used with a lot of different sorts of like meteorological data and that sort of thing, some aerosols. Do you see sort of coordinating with even like other areas within the geosciences, or do you think this is pretty like convective, community focused? Yeah, how do you see sort of moving forward with that?
I mean, I can see this being used to track. I mean, for example, I gave one where they've already done some tracking air quality, so it's not just for convection. It's for. I mean, you could even go look at, for example, if you had a region of enhanced aerosol, like if you want to track a part of the Saharan air layer, you could use something like this and then try to track where it's going. So, I right now, a lot of our example cases are convection, but there have been some that we've used for air quality as well.
Great. I see a question in the chat. So does Tobac track cloud shape? If so, how do you do it?
Can you repeat?
Does Tobac track cloud shape, like the shape of the cloud? If so, how do you do that?
No, Tobac does not consider shape of the cloud explicitly, but the contours are used for tracking. That nothing is saved there. In the other algorithm where there is TINT, we are using area. There are some shape parameters that we compute while doing the tracking, but at this time they are not included in the cost function because there was no need to include that in the cost function. It just turned out that it was working without looking at shape, because if you want to keep the shape constant or think that the shape is something that will be used to identify this object in the next stage, then cloud change their shape very quickly as they start evolving. So shape is not the parameter in the cost function. But we had this in the earlier, I won't say it was in the version, but while developing this was a thought, and it just turned out the shape changed very quickly.
Then a question from Ryan. So could you use it to track ocean eddies? Example based on sea surface height or temperature fields?
Yes, that is what exactly I was about to say when you asked that whether this is only for convection. So this is for any convection-like object, because this is object agnostic. So when you look at the algorithm, it doesn't know what it is tracking. It has a two-dimensional array, and then it has some features in there. So any feature can be tracked. So it is not considering any, what I want to say is that it's not considering any meteorological or physical characteristic of the object. And the only characteristic that it looks at is the shape and the area that it is covering and the speed with which it is moving, which can be given. You can literally track cars using this, but obviously if there are two cars going from nearby each other, it will say they merge and split because that's what it is trained to do.
Great. And then a follow-on to Tyler's question, which is the Tobac track cloud shape question. Can you track motion that includes feature rotation?
It will track the object. It will not consider rotation. It will not know that it's rotating. And for the shape also, I'm actually working on one of the projects where one of the summer student is working, and she's computing some shape parameters for different clouds using morphological image processing. And if that turned out to be a good measure for identifying organization of the system or something, we'll probably add that into Tobac later.
Great. Any other questions?
I'll throw a quick softball to help expand on that question. So Bhupendra, can you elaborate a little bit more on how an object is identified? Like, is it a binary field that you said? How do you actually create the mask that is what is tracked from frame to frame?
Okay, so as I said, the Tobac gives you a lot of flexibility, and we currently have Tobac method plus TINT method, plus we have other method that I want to track. So how we identify object here is in the Tobac, we have multiple thresholds. And the objects are identified using thresholds. So you can choose the threshold, or there are fixed thresholds, and it will work with those fixed thresholds. In TINT, you can basically identify objects using any of the custom method that you like and give that as an input. And you can do the same thing with Tobac, because then you just skip the first stage and go for the tracking directly. So that is the advantage of being modular. You can add your own pre-processing and post-processing, and you just can use it for tracking itself. Thank you.
Great. Thanks so much. Let's give him another hand.